Okay, so what's the concentration in the tank in terms of Q volume? It's Q over V, isn't it?
Right.
Well, that equals then Q over V times 5.4 gallons per minute. Okay? And then the net rate, well, how are you going to get the net rate if you know the rate at which solute flows in and the rate at which it flows out?
Then that's where you just have to subtract those, don't you?
Yeah.
Yeah, okay.
Yeah. So it's just the rate in minus the rate out.
Right.
Well, the net rate is the rate of change of the amount of solute, that's dQ dt.
Right.
So the equation then is simply dQ dt equals 0.021 times 5.4. Understanding that this is all in gallons per minute, we'll leave the units off, although it's always good to write them. Minus Q over V times 5.4. Okay? Well, that's a very easy equation to solve. It's first order linear, among other things, but it's also separable. Okay? Actually, is it separable? I think it isn't. But yeah, you put all this over V, and suddenly you've got a V minus Q in the numerator and a V in the denominator, right? And you can't separate the Q from the V. So you have to solve it as first order linear non-homogeneous. That is, it's Q prime minus P of V times Q equals, what symbol did we use? I think we might have used Q, which wouldn't be a good symbol to use. But that equals 0.021 times 5.4%, right? Which is approximately 0.11, very close to 0.11. Okay? So you solve this accordingly. Okay? Integrating factor is going to be an antiderivative of P of V with respect to V, and it's not P of V, it's P of T. Integral P of T with respect to T, and, well, P of T is just a constant. It's 5.4 over V, right? Okay. And it's, of course, e to the integral of that. Okay? Multiply that, the left-hand side becomes just a differential of a single expression. And you have it. Okay?
Okay.
And you know that technique, 'cause that's one of the earliest techniques that we dealt with, and I assume that you're real familiar with that.